Abraham from the University of Toronto. Bob got his PhD at Oxford and then was a postdoc at the Hertzberg Institute and the Institute for Astronomy at Cambridge, the other Cambridge. And
real
then he
Cambridge.
was the real Cambridge? Oh, I didn't say that. Sorry, he said that. I'm just echoing things. And then he moved to a professorship at the University of Toronto where he is today. Bob has won numerous awards, including the Premier's Research Excellence Award and the Stacey Fellowship up in Canada. He is one of the world's experts in the field of extragalactic observations, and today he's going to tell us about some exciting work that he's been involved in the past few years in the low surface brightness universe. Take it away.
Thanks, Charlie. How's the sound? Is that okay? Right. Okay, so once upon a time, the University of Toronto had an archaic observatory. This was on the outskirts of town, so it was sitting on 200 acres of prime real estate in the fastest growing municipality in Canada. So this genius, Peter Martin, who is probably known to some of you as the person who founded CETA, figured out a way of turning this old observatory into huge piles of money to found this thing called the Dunlap Institute for Astrophysics, whose goal, is essentially to be an instrumentation analog to CETA. All right, so the idea is to focus on the development of novel and cutting-edge instrumentation. So to continue this story, okay, more or less at the same time, I found myself on, the board or advisory committee for, Canada's a very small community, so I found myself on the board or advisory committee of everything. Okay, Canada's involved in, Gemini, JWST. It was sort of depressing, okay, seeing how, we're planning the future, and the future takes forever to materialize, okay? So, you want a new Gemini instrument? Fantastic, show me your $80 million and show me 7 or 8 years of your life, and then it'll appear, okay? So at that point, I began to look like this fellow, all right? And so this is Sir Karl Popper. So at more or less the same time as I'm having this angst, okay, about instrumentation, here we are, I'm helping Peter Martin to develop the vision for this new institute focused on instrumentation. But at the same time, I'm sort of losing faith, okay, in the idea of whether or not, we can couple this to our graduate program, right? Because I'm in charge of our graduate program. And so how can I make this relevant to students, who are around for 5 years and, need results fast. And yet we're building these things. We don't trust them because it's $100 million. They last, 8 years. We don't want them around for 8 years, right? In the lab. So it's a problem. And, it becomes worse. Okay, this is a tale of woe. It becomes worse, okay, because at that point, because I'm in charge of the graduate program, I'm expected to give inspiring speeches to the graduate students, okay, on the subject of how to do science. And as an observational cosmologist, I felt, I should go back and read Sir Karl Popper's book, the Logic of Scientific Discovery, page 1 of How to Be a Scientist. And Sir Karl says to do science, what you do is you test a prediction, okay? And that's not what I do. And at least half of the people in this room, if you're observers, that's not what you do either. All right, so we're not testing predictions because the predictions in my subject are too poor to be worth, falsifying. Okay? So that provocative statement, okay, is clearly telling you where I'm at, okay? This is, now we're winding the clock back about 3 years. It is clearly some sort of a midlife crisis. So at this point, I get a visitor who comes and it turns out, and this visitor is familiar to you, Peter van Dockum at Yale, and he's having exactly the same crisis as me, okay? And so we decided that together we would chart a way forward, okay? And it's going to involve discussion over beer. And we decided over this beery conversation that we were going to do something new. Okay? And it was going to adhere to a couple of precepts. And it was going to have, some constraints. Okay? So it wasn't totally unconstrained. But the precepts or premises were that we were going to come up with some observational scheme that would be focused on testing a concrete prediction of theory for how galaxies assemble. Okay, now that's actually a challenge, right? Because most predictions are so fluid, that you can just twist a knob trivially and you can explain away most things. And so why is that? Well, it's because, galaxies, at least in, our conventional theories for how these things, assemble, are mostly dark matter, and the things you observe are mostly stars. And so, you can explain away many things by just simply adjusting what's going on with the baryons and ignoring what's going on with the dark matter. So, okay, so we're gonna identify a prediction. So if you're working in this area, you should think yourselves, okay, what central prediction of hierarchical galaxy formation models, is worth falsifying, right? So the next premise, okay, is that at some level, even though we're inspired by Sir Carl, we're not going to be slavishly adhering to him, okay? Because one benefit of being in this subject is it's still possible to be an explorer. Okay, so exploration of this kind is not really in Sir Carl's book, yet I think it's a completely legitimate mode for us to be in if we can identify, particularly easy, if you can identify an unexplored bit of parameter space and just go there. Okay, so that's the ideal case, is we're going to be testing some theory by looking in an unexplored bit of parameter space. So those are the premises, and the constraints are that it's okay to fail. Okay, we're going to be inspired by Silicon Valley, but you can try something crazy and it can be a failure, but it has to fail fast, okay? So it's just like, a Silicon Valley startup. It can be risky. Ideally, we're going to build something, and it's going to be something that we can, by throwing in resources from Toronto and Yale internally, we can do it for a few $100K, because that's sort of, money you can find in the sofa, and you don't need to, get onto the treadmill of applying for grants, and that takes a long time because we want to do stuff fast. Okay, so this is going to last 3 years, so we're closing in on the end of this plan because this conversation was of order 3 years ago, and we're going to do it ourselves. So no Army of postdocs, no grad students. The whole point is we're trying to, bring back the fun, okay? We're going to do this ourselves as a hobby. So what's this thing? Okay, so let's go back to the first question, okay? What is worth falsifying, okay? What can be tested without adjusting knobs? So, after enough talking and thinking, we convinced ourselves that there were two problems, okay? The missing satellite problem and the missing substructure problem. And I'll go over those quickly in case they're not familiar to some of you, although I expect that most of you will know what those are. So I assert today, okay, that these are basically the acid tests of hierarchical galaxy formation theory. And although neither Peter and I have worked on these things in the past, we've just decided that we're going to work on them now, okay? So the missing satellites problem. Well, hierarchical galaxy formation is a scale-free theory, right? So if I hadn't told you, you would not know that this was a numerical simulation for a cluster of galaxies, and this is a numerical simulation for an individual galaxy, right? So if you don't know in advance what scale you're looking at, and if you're just looking at the dark matter, you can't tell. Right? So that manifests itself as a prediction for the number of satellites around nearby galaxies. They should be distributed in terms of mass in a way that's connectable to the distribution in terms of mass of such things in rich clusters. So is that what we actually see? Well, if you look at the distribution, so this is a distribution as a function of a parameter that's basically mass, okay? So this is a distribution of galaxies in a simulation of the Virgo cluster here. This is the Virgo cluster data. It's a beautiful agreement with the data. If you look at the distribution of nearby dwarf galaxies around the Milky Way and Andromeda, you see that the correspondence is incredibly poor. Okay, so that's the missing satellite problem. And it's, at least a factor of 10 and arguably a factor of 100. We just don't have enough satellites. So perhaps, I was showing you something from 1999. This problem has gone away. It hasn't, okay? It's just as bad now as it was then. This is from a more recent paper and comparison of what is predicted with the actual distribution of Milky Way dwarf spheroidals. So, is this a huge failure? Why are we still believing in hierarchical galaxy formation? Well, the reason we still believe in this stuff is because there's an expectation that the problem is in the observations and not in the theory. Okay, because there's a potential here for huge biases. So if you look at the distribution of dwarf galaxies in terms of absolute magnitude and distance from the Milky Way, you see that they occupy this bit of parameter space here, which nicely corresponds to the detection limits of Sloan. If you then translate that into a surface brightness limit, what you get is this. Okay, so this is a size of the dwarf, and this is how luminous it is. This line here corresponds to 30th magnitudes per square arc second. Okay, so it's certainly plausible, all right, that the universe is just locally is just peppered with little faint dwarf galaxies that we're just not detecting, simply because we're constrained to look for them using instruments that are only sensitive to high surface brightness things. So maybe it's just a huge bias. Right, so the missing substructure problem is related. Okay, and it gets to the heart of the theory, again, because it's a theory of coalescence, okay? We've got a dark matter halo with a ton of substructure, and that substructure is merging to form bigger galaxies, forming bigger things from little things. So if you look at the predictions from numerical simulations, this just happens to be, one from a huge, set of possible simulations, all of which would more or less show the same thing, but I happen to like this one for a reason I'll explain in a moment. You'll see that there's an expectation that if you look at galaxies at a low enough surface brightness threshold, galaxies should not resemble the smooth, symmetric, archetypal forms we're familiar with. Every galaxy should look like a squashed bug. Okay, so the key thing, though, is you have to look at a low surface brightness level. So in this simulation by Johnston et al., the nice thing about this is it shows the simulation rendered from outside and from inside. Okay, so if you were inside this thing and you were constructing a all-sky survey, akin to Sloan, you'd expect to see streams and other, knots of structure. If you're on the outside, you'd expect to see streams and knots of structure. But in both cases, those streams and knots of structure should be at surface brightness levels that are, on the whole, undetectable. Okay, so for reasons I'll quantify in a bit, it's very difficult with conventional telescopes to image at surface brightnesses below, say, 27th magnitudes per square arc second. So really the bit of this thing you actually would see with most imaging campaigns is just the inner bit, and you would fail to detect all of the structure. So does this mean that it's hopeless, that that these simulations are completely unconstrained? Not at all, okay? Because in cases where you can resolve the individual stars, you can bin them up, and you can get to surface brightness levels that are down around here, that are quite comparable to the regime probed by these simulations. So at least for very nearby galaxies, including the Milky Way, okay, you can do this kind of thing. So this is a beautiful result from pandas. Okay, so it's done from star counts, right, where you actually resolve the stars and bin them up. You can see that this has a wealth of structure, probably not at the level predicted by the simulations, but nevertheless, you can see things like the giant string. In the case of Sloan, of course, there's the famous and familiar field of streams, right? Where, again, resolving individual stars with known stellar populations and bidding them up, you can identify these, these beautiful streams. So this is, in terms of equivalent imagery, probing down around here. Okay, so the key thing in this talk is asking yourself why you can't just take pictures of galaxies and get down to those sorts of levels. Right? So there's misleading stuff in the literature that suggests that you can, but it is not true. Okay, so here's a beautiful image taken by an amateur astronomer with a 6-inch telescope. So first thing to note is I said a 6-inch telescope. Okay, I didn't say Keck, I didn't say HST, right? So there, this is clearly probing low surface brightness structure on galaxies. So there's this is the first hint in a theme that I'm going to develop, right? That size doesn't always matter. All right, so 6-inch telescope. And you can find examples of this in the literature. Well, people will point to this sort of structure and say, aha, you can compare this to the Johnston et al. Simulation. You can see that we are now witnessing with our very own eyes the predictions of these numerical simulations. No, okay, that's completely not true, because this structure, although it's very faint, is really only, sort of 27th, 28th magnitudes per square arc second. So this is what people refer to when they're talking about ultra deep imagery, okay, 27, 28. But it's still several magnitudes per square arc second away from the debosh of structure predicted from those simulations. Okay, so this is an example of a galaxy eating another galaxy, right? But this isn't an example of, the sort of substructure associated with those simulations, where really, the mass differential between the big thing and the little things is much larger. Okay, so that's not what's referred to with these simulations. So perhaps the missing satellites are there. okay? Perhaps the streams predicted by these simulations are there, but nobody's seen either. Why not? Okay, why can't we see them? So maybe they're just at too low a surface brightness. Why can't I just get down to the required surface brightness level? I, write a time application for Gemini, and I want to see something and it's fainter than what my last application. I then ask for longer integration time, right? Or I say, well, Gemini is never going to be able to let me do this in a practical amount of time. I need a 30-meter telescope, all right? So that's the cure that we've, been using for the last 100 years. Okay, if you need to see something fainter, you build a bigger telescope or you're exposed for longer. Why can't we just do that here? So I assert that you cannot, okay? And I will furthermore assert that that is because this is a really hard problem that has made really zero progress in the last 40 years, okay? So you can go and look up this paper by Cormandy and Bacall. It's from 1974. Okay, and the faint envelopes of galaxies that these people were exploring have surface brightness limits of between 27 and 28 magnitudes per square arc second, exactly like the thing I just showed you, right? You can use the Canada-France Hawaii telescope. You can do deep imaging with that, and irrespective of how long you integrate, that's the surface brightness limit that you're going to hit. So what's the problem? So the problem is you're not limited by photon statistics here, right? What you're limited by is systematics. So if you want to beat this problem down, you need to figure out a way to eliminate systematics. You can't solve this problem with a bigger telescope. You can't solve this problem by integrating for longer. So what are these systematics that I keep talking about? Okay, let's quantify them. And I'm going to assert that the basic problem here is that the systematics that are bedeviling us here are the same ones that make it possible for us to build large telescopes. Okay, so Optics 101, okay, I want to image something at low surface brightness. This is the governing equation, all right? So this is basically only relevant if what I'm trying to do is resolve a low surface brightness thing that's much bigger than, the seeing scale. So this is not at all the right equation to use if I'm trying to, determine the faintest star I can see in my image. In that case, I have an equation that has a parameter in here, which is the aperture of the telescope. But in this case, where I just want to see a very extended low surface brightness thing, I use this equation, and nowhere in this equation do you find any term that corresponds to the aperture of your telescope. Instead, what you have is a term that corresponds to the focal ratio of your telescope. Okay, so the governing equation here for the amount of light you get, depends on the focal ratio to the -2. So what you want is a fast telescope. You don't want necessarily a big telescope. What you want is a fast telescope if your goal is to image low surface brightness structure. So let's look then at what I would argue is the best telescope. Well, no longer, but up until a couple of years ago, this was the best telescope on the planet for this kind of work. This is the Burrell-Schmidt telescope on Kitt Peak, which is optimized for these sorts of observations. This is a beautiful image of the center of the Virgo cluster taken by Mijos and his collaborators. Structure here is going down to like around 29 magnitudes per square arc second in the B-band. Beautiful image, okay, taken with this telescope that's been optimized for this kind of work at the level of taking skinny graduate students and sinking them into here with blowtorches so they can move stuff around and paint the interior of this thing with exotic Italian optical paint to minimize scatter. They've really taken exquisite care to optimize this telescope for these sorts of observations. It's a Schmidt telescope, so it's very fast. So what's the tall pole? What's limiting this thing from integrating for longer and getting down below, say, 30th magnitudes per square arc second? Well, the thing that's limiting this is scatter and diffraction. Okay, so this is a picture of a 0th magnitude star, and the star is at different positions in the field, and you see it's got this enormous halo. That enormous halo is internal scatter from optical surfaces and from filters. In the case of this beautiful paper, what these clever people were able to do is ray trace this stuff and then subtract off a model of the scatter and of the diffraction, and are able to improve the detectability of structure, which is it's a tremendous amount of work, but they succeeded. Okay, so even after doing this, okay, what are we left with? Well, if we look at the contamination of the light on these Schmidt images as a function of apparent magnitude. So this is 29.5, and this is the fraction of pixels contaminated at that level. At 29th magnitude, around half of all those pixels are dominated by scattered light, okay, from background galaxies, foreground stars. At 29.5, you're fully contaminated, right? So that's the reason why you can't image below the surface brightness, okay? You've hit a wall, and that wall is basically scattering and ghosting. Okay, so, that's an archaic telescope. That Burrell-Schmidt is not at all, a familiar optical design. So let's look at some other optical designs. This is a beautiful Vista telescope. First thing to note is it's stubby because it's fast, and it's got a huge secondary mirror. So let's look at other optical designs. This is a Large Synoptic Survey Telescope. Very, very, very clever optical design, but it's stubby because it's fast. Has a huge secondary mirror. It even has, because of the clever optical design, huge bits of the primary that actually are bigger than the secondary that act, as a pupil stop. So, the effective area of this thing is defined by this. So, everybody's favorite telescope, Sloan, it's a little older, so it isn't quite as fast, but it also has a huge secondary mirror. So what's going on here? Well, what's going on is if you have a reflective Cassegrain telescope, you need a big secondary obstruction if you want a wide field of view. Okay, so, I assert that I need a survey telescope, I need a wide field of view, part and parcel of that is I need a big secondary obstruction. Big secondary obstructions optically, again, optics 101, they're bad if what you want to do is concentrate light. So if you look at the, and this is the perfect case of a seeing limited observation, where if you were unobstructed, 80% of the light would be within the airy disk. Well, within the airy disk. As you make the secondary obstruction bigger, you start launching more and more of the light off into the wings. Okay, so you can quantify this in terms of the modulation transfer function. That's done here. The point is, on large scales, as you go to lower and lower frequency, the problem becomes worse and worse. You don't care at all if what you're interested in looking at is a compact galaxy or a star. At high frequency, your performance is essentially equivalent to the theoretical performance of the aperture of the mirror. But at large scales, you're limited, in contrast, by the mere existence of a secondary obstruction. Okay, so that's bad, right? But it gets even a little worse. So if I illuminate a surface coated in aluminum, hit it with a laser, and then I look to see what the scattered light looks like off that mirror, I can notice that there's a ton of scattered light. And that can also be quantified by something called the bidirectional reflectance distribution function. And the point is, the mirror is not perfect. Okay, the mirror has surface irregularities and roughness. It's inherent in polishing this thing and coating it in aluminum. So reflective surfaces are poor if your goal is to avoid scattered light. So that's terrible. I've just described the two key things that are associated in big telescopes, right? A big mirror with another mirror. That's a big telescope. So what am I talking about? Am I saying that optical design is fundamentally wrong? Not at all, right? Because in most cases you don't care about the ultra low surface brightness universe. You don't care about scattering and ghosting at the level where it isn't a tiny portion of what you're trying to achieve. But if that tiny portion happens to be what you're interested in, conventional optical designs are limited. Okay, because of diffraction from secondary obstructions and micro roughness in the reflective surfaces. Not to mention other practical things, which I don't have time to talk about, like dust on a mirror. Okay, so what's the cure? Well, there's one obvious cure. It sounds crazy. Okay, so here's one cure. Okay, so this is the Yerkes 40-inch telescope. You might recognize that familiar face. So this is built at the tail end of the 19th century, right? So, am I advocating going back, 120 years, to the apex of refractor technology? Well, these things have been dead, for a century for a reason, right? So for one thing, remember the other thing I was trying to optimize for, speed. So this is a f20, right? So it's clearly not what you want, right? Okay, so maybe that's not what you want, but maybe the world hasn't stopped in terms of the development of refracting telescopes. Maybe it's just gotten a different name. Okay, so it turns out that although refracting telescopes have been dead to astronomy for over 100 years, in the real world of non-astronomy, the development of the technology behind these things has been proceeding at a furious pace over that century. It's just we don't call them telescopes; we call them telephoto lenses. So this is the world's premier telephoto lens. It's a Canon 400 IS. So this is the premier telephoto lens if you're a paparazzo. Okay, and your mission is to photograph Barack Obama with his shirt off. That's your weapon of choice. So maybe these are the way to go. Well, maybe not. Okay, and the reason maybe not is because if you actually look at the optical design of these things, it's terribly, terribly complicated with glass surfaces that are aspheric and have, huge curvature. And those things are bad in terms of ghosting. And furthermore, these optical coatings are not perfect, right? And so, the ghosting wouldn't be a problem because these things are, well baffled. But the ghosting might not be a problem if the optical coatings were perfect. And so they would work at high angles of incidence. But, conventional optical coatings, they're not that, they're good, but they're not that good, right? So it sounds like this is not the way to go. But I just lied to you. Okay, so I was not familiar with this, but it is nevertheless true that there has been a revolution, okay, in optical coating technology. There's now a family of coatings called sub-wavelength nanostructure coatings that are just now beginning to appear on the ultra top end of commercial lenses. So the way these things work, it's actually it's tremendous fun. Okay, so this is a wavelength of light, and these coatings are like little cones. Okay, so as the light propagates, it hits the tip of the cone, and essentially imagine sort of Swiss cheese, okay, where you've got lots of little holes. So you're averaging over the Swiss cheese in terms of the dielectric coating here, and so the index of refraction is some sort of average over the tips of the cones, but mostly it's air in between the cones. Then as it propagates through a little more, you intersect a bit more of the cones, and then the average encompasses more of the cone and less of the air. By the time you get to the bottom, you hit the base of the cone, and the whole thing is just a dielectric. Okay, so since you're averaging over many cones, because that's the wavelength of light, the equivalent here is that the wavelength is propagating through to the glass. It's effectively a continuous variation in the index of refraction, which is the magic bullet for perfect optical coatings. Okay, so provided you can figure out, and this is some hyper secret known apparently only to the Canon technology engineers, and it's unpublished, and I have no idea how it's done, but provided these things can be made, there's a potential for perfect optical coatings. So these are conventional, really good multi-reflection coatings. This is reflectance as a function of wavelength, and these are pretty good. The reflectance here is say 0.5%. But the equivalent one for these, magic coatings, it's essentially perfect unless you get to like really high angles of incidence. It is, it's really perfect. So there's, a revolution happening, that astronomers as a rule don't know about because we aren't really that plugged into cutting edge instrumentation. And so that's part of the ethos of this Dunlap Institute that I was telling you about. By bringing these two communities together, can you build better astronomical instruments? And so I think the answer is yes. Okay, so this happy person has got a goofy grin on his face because this thing is $12,000. Okay, so that's what one of these lenses costs. So this guy has got a goofy grin on his face. So my friend, and presumably many of your friends, Peter Van Duckum, who says to me over our beery conversation, so I'm now circling back to the start of this talk, he says, I bet these $12,000 lenses with their special coatings would be really good for astronomy. And I say to him, Peter, yeah, sure. Yeah, it's pathetic how you Canon fanboys believe everything you read. Put your money where your mouth is, smart guy. He's really into photography and knew all about these lenses. I'd never heard of them. He'd heard about them because he'd read the Canon ad, where they talk about these magic coatings. Okay, so at that point, it was beery conversation, macho BS. We're just going to do this thing. Okay, so we bought a lens. And we started our adventure, okay? So we bought a lens, 50-50, Toronto, Yale, and then we decided we were going to test this thing. Where do we go to test this? Okay, so, wow. So our journey, okay? My journey starts in Toronto. This is the University of Montreal has an observatory at Mont-Mégantic in Quebec. And so we decided that we would go there because it's kind of equally inconvenient to get there from New Haven and from Toronto. Okay, so we drove there, and I borrowed a CCD camera from our undergraduate lab, and Peter borrowed a mount from the Yale undergraduate lab, and we stuck it up there, and we shirked our administrative duties for a weekend, and we started taking pictures of things. And it was remarkable. I think, I at least, as I, alluded to in the little cartoon, was assuming that Canon was lying. And Peter was, for some reason, assuming that Canon was telling the truth. And Peter was right. Okay, so this is a picture of NGC. It's just a random group, okay? It's a 20-minute integration. To just test this thing properly, we also brought along a lens of the preceding generation without the magic coatings. And so this is without the sub-wavelength nanostructure coatings. This is with the sub-wavelength nanostructure coatings. It's quite a difference, right? So the point is, in this case, you can integrate longer and you're just getting more data. Here, you integrate longer, you're just getting more halo. And these are stretched very similarly, okay? So that was encouraging. And at that point, we thought, this is going to work. So then, we start really thinking about what we can do that make a big impact. And so, you don't just want one lens, right? So really what you want to do is use a bit of math. And the math tells you, okay, that the equivalent aperture of this thing is the square root of the number of lenses you have multiplied by the aperture of an individual lens. So the aperture of an individual lens is almost 6 inches. Then the equivalent focal ratio of this thing, because all these things are pointed at exactly the same spot of the sky, okay? So it's not like WASP or something, or super WASP, where they're pointed at different places. All pointed at the same thing. Okay, so the equivalent focal ratio is the focal ratio of an individual lens divided by the square root of the number of lenses you've got. So in this configuration, Dragonfly is currently a 0.4 meter f1 refractor. But no, okay, because another beautiful aspect of this plan is that every time you've got $15,000 to pay for a new lens and a CCD camera, you bolt it on. Okay, and so when you bolt it on, you make your telescope bigger and faster. So, we just a couple months ago, we had an extra 30K and we bolted on another couple. And so Dragonfly is now a 0.46 meter f0.89 refractor. So this is a 300-second integration. This is the equivalent, but by adding up, all the light from all the lenses of a 354,900 second integration. So many nights. And you can see that you are still, this is just a tiny portion of the frame, okay? So it's not a full frame, it's a tiny portion. You're not yet at the regime of being dominated by these halos. And you can start to see structure like this WASP of Cirrus, which I'll talk about later, or Cirrus being the enemy, that is down around 30th magnitudes per square arc second just by imaging, okay? So this is what it looks like from the back. And it's got a 2-degree by 3-degree field of view with these, commercial, inexpensive-ish Pro-Am CCD cameras. It's, resolution is poor, okay? It's like 3 arc seconds per pixel roughly. And this thing's fully robotic, okay? So the graduate students program it in the afternoon. They set it going, and then the next day you come back and you pick up your data. Okay, so no human intervention involved in getting the data other than writing a script in the afternoon. So, being scientists, we didn't want to just believe the Canon ads, and we didn't want to just take pretty pictures. So we actually looked at the distribution in the wide area, or the wide angle PSF, and compared it to the Burrell-Schmidt, the world's best telescope for this work. And so this is the log normalized flux for a star imaged with the Dragonfly array. This is for the Burrell-Schmidt, putting it in surface brightness, magnitudes per square arc second units as a function of log radius. This is about 1 degree. We're almost a couple magnitudes better than the Burrell-Schmidt at wide angles. Okay, so it's about a factor of 10 better than the world's best telescope at large angles. So, potentially a revolutionary science, but the bad news is I lost my bet with Peter. So, it's bad. So this was independently confirmed by other people, but I won't describe it. Anyway, okay, so what's the tall pole now? Well, the tall pole now, if you start taking pictures of random bits of the sky, is clearly the galactic cirrus. Okay, so this is what you get with actually, medium latitude field, so not pointing near the plane or anything, but this is a 1-hour integration of just a relatively random group. That's what the full moon would look like in terms of equivalent area. You see, the issue here is the galactic cirrus. So if you're going to make progress with this, Dragonfly puts you in a regime where you have to carefully control your sample, because otherwise all you're doing is doing the world's greatest Cirrus survey, and that's not what you're after if you're trying to study the galaxies. So Cirrus has become the enemy. Okay, and so at this point I have to confess that this started off as a hobby, and we swore to ourselves that there'd be no students and no postdocs, but it's kind of just gotten too big, okay? Because we, went from nothing to this, 0.89 half-meter telescope with this survey that needs to run, every night, and it was just too much for us. So we've now taken on some students, and we've embarked on a survey. I'm not going to give you the results from the survey yet because we're halfway through, but I will give you some highlights, okay? And the key elements in this survey are careful control of the galaxy sample, okay? The pretty pictures of, nearby galaxies that I was showing you earlier are biased because they're done by amateur astronomers who want to take pictures of spectacular, pretty-looking galaxies with tidal streams and mergers, okay? But, our mission is to pick boring galaxies, fairly selected, and the only slightly strange element of our selection for our survey and our plan is to do 20 to 30 galaxies over a course of 2 to 3 years, is that we have to first identify regions of the sky with very low Cirrus. So we're essentially looking in holes with very low Cirrus as identified by IRAS 100 micron maps. And the people that are now doing the actual work are graduate students Alison Merritt at Yale and Jayli Zhang at the University of Toronto. So the students are, as always happens, the students are doing the actual real work now. Okay, so highlights. I'm just going to give you a couple of highlights, or 3 highlights from Dragonfly. So let's first go with, we did Optics 101, now let's do Spiral Galaxies 101. Okay, the 2 basic facts about spiral galaxies is that the stars in spiral galaxies are distributed in an exponential distribution, and the visible wavelength imagery of spiral galaxies is usually half the diameter of a deep radio image of a spiral galaxy. So the H1 typically extends to twice the size of a visible wavelength picture of a galaxy. So these things have exponential disks, but if the hierarchical galaxy formation model is right, eventually these exponential disks have got to turn up because you're in the regime of the stellar halo. Okay, so are we seeing that? So few examples. So this is M101. So this is, I guess this is the world's deepest image of M101. The structures you're seeing out here are about 29th magnitudes per square arc second, and they were first found by Mijos and collaborators with the Burrell-Schmidt. But Mijos and co. Don't go quite as deep as us, and they don't analyze the data in quite the same way. And so the sort of stuff that I'm going to show you in the next few slides is new to us. Okay, so this appeared in a paper by Van Dockum et al. About a year ago now. Okay, so this shows a surface brightness mass density profile. This shows a mass density profile for M101 as a function of projected radius in kiloparsecs. So this is the mass density in solar masses per square kiloparsec. At the limits of the data here, it's actually crazy. So this is like 100 solar masses per square kiloparsec, which corresponds to about 34th magnitudes per square arc second. So we're about 12 magnitudes below sky here, and we're about 5 magnitudes lower than typical profiles for this thing. And so the point is, even though we're extending so much further, it's well described by an exponential disk out to the limits of our data. At the level where we can basically put a limit of about, say, 0.5%, in this case it's 0.3%, on the mass contribution from an extended stellar halo. So if you compare that with the Andromeda Galaxy, the stellar halo in the case of the Andromeda Galaxy is 5 to 15%. Okay, so whatever's going on with M101 built up the gigantic disk in M101, which is about as big as the disk of the Milky Way, in a way that did not build up a stellar halo, which is, the acid prediction of a hierarchical galaxy formation model. So M101 is a strange galaxy. It's strange in other ways. Now I've just given you an additional strange thing about M101. So let's compare this with the predictions of numerical simulations. So this is the stellar halo mass fraction relative to the total stellar mass of the galaxy. Okay, so this is the total stellar mass on this axis, the stellar halo mass fraction here. That's where M31 would be, where the Milky Way would be, where M101 would be. This is a comparison from a numerical simulation, and we've just added our point to the data from Cortot et al. But who believes any single numerical simulation? So this is what happens when you put this on another numerical simulation. This is kindly given to us by Cooper. So this is the Cooper et al. 2013 numerical simulation. This is the predicted relation. This is 1 sigma, 2 sigma. This is where M31 and the Milky Way lie, and this is where M101 lies. So it's not within the envelope of the 2 sigma relation, but maybe it's just a 2 sigma galaxy. So can't do very much with a single object, which is why I think the survey, when completed, will be really exciting. But I can't assert that M101 certainly does not correspond to the sort of numerical simulation that I was showing you earlier. M101 has a giant disk and hardly any bulge, so as I said, take it with a grain of salt. It's weird in other ways, but certainly it's extra weird in this particular way. Another example. Okay, so this is the archetype for a class of spiral galaxies known as flocculent spirals, where they clearly have a spiral structure, but it's not grand design in nature. And if you look at the dynamical aspects of this galaxy, grand design spiral structure cannot exist because the Tourmaret instability criterion is not met anywhere in this thing. Okay, so how can it have spiral structure? Well, the assumption is that this spiral structure is not being set in motion by density wave. Instead, it's being set in motion by something like star formation and shear. So, in any case, this object has an unusual, but not super unusual type of spiral structure, and this is an image of this thing taken with HST. The best image of this thing that I was able to find was actually taken by an amateur astronomer, not with HST. Again, it gets back to this earlier issue, right? If what you want to do is look at low surface brightness, size doesn't matter, okay? Other things matter. So this is an image of NGC 2841 taken by an amateur astronomer. I'm going to lay down a circle here at D25. Okay, that's a conventional galaxy size corresponding to the usual definition for the diameter of a galaxy, roughly corresponding to how far you can see with a deep image. I'm going to point out that there's a handy reference star here to guide your eye that lies right on that D25 ellipse. Okay, so let's compare this with the radio data, okay, which I assert extends to about twice the visible disk of this thing, and with the Dragonfly image array. So, and I'm going to do that in 2 ways, okay? Firstly, I'm going to do it by turning it to 8, and then I'm going to turn it to 11, all right? So let's first turn it to 8. Okay, so this is there a way to make this room a little darker, Charlie? To heck with it. I think it'll be okay this way. Is there... yeah, let me set in motion a chain of events that I'll regret. Okay, so this is just shining on me, but not on the screen, so it's probably better. Okay, so this is a... it's okay. This is probably... oh, yeah, now we're talking. Okay, so this is this is going to screw up the video to a large extent. Okay, never mind. Okay, so this is the reference image. And so this is a Dragonfly image that I've histogram equalized. So that's an image processing technique I don't have time to describe. Okay, but in any case, this corresponds to D25. And so the first thing that emerges from our, turning it to 8 thing is that, well beyond the visible disk from, even the deepest image of this thing I could find on the internet, we're going much, much further. And we're seeing a debosh of structure, including, and interestingly, what appears to be either a bunch of rings or, excitingly, grand design spiral structure, which cannot exist. Okay? So, I think that's really remarkable. So you can see we're going further, but it's more interesting when you can then compare this with radio data. Okay, so this is a deep H1 map from the THINGS survey. You can see that the visible wavelength stellar imagery maps on very nicely onto this radio structure. Okay, so whatever's going on here, is forming stars in a way that is well connected to the neutral gas, which is interesting, right? Because stars are not forming in neutral gas; they should be forming in molecular gas. So what's going on? How did those stars get out there? Okay, so that's quite interesting, but really we haven't really turned it to 11 yet. So let's do that. Okay, so I'm not histogram equalizing it. I'm just using the beautiful CFA produced tool DS9. The props to you guys. Okay, and just stretching this. All right, and so the point here is that if you really just stretch this and do nothing unconventional in terms of image processing, the starlight stretches out to the same extent as the radio data. Even, and the concordance is really beautiful. If you look at this, I don't know what to describe that, a jet or a streak? But anyway, you can see how it maps beautifully onto the starlight. So what's going on here? Okay, stars seem to, so we're breaking the rules here, okay? The starlight is stretching out to the full extent of the radio data, but that radio data is neutral gas, right? So what's the starlight doing there? So maybe it's not starlight. There's, one possibility, and this is a suggestion that Bland Hawthorne and collaborators have thrown out there in the context of NGC 300, that instead what you're seeing is scattered light from dust embedded in the neutral hydrogen. Well, that's interesting. So we're looking into that, but it kind of, only brings up another question. What's the dust doing out there? Of course, because the dust originates in stars. Right, so either way you look at it, somehow we have to associate starlight with neutral hydrogen and not necessarily with molecular hydrogen. So that's really quite a puzzle. So the other thing, if you believe, and I'm not sure I do, okay, but if you do believe that the stuff I showed you in the previous slide was grand design spiral structure, what's it doing there? Okay, because locally, perhaps the tumor instability criterion might be met. In which case you could get some star formation driven by spiral arms, but somehow you have to excite a gigantic mode of spiral structure in this thing, and this thing is quite isolated. So it's interesting, and I'm afraid I'm not going to be able to give you an answer, okay? But instead, I'm presenting you with a question. How can we have this galaxy doing what it's doing? I don't know. I think in the interest of time, I'm going to blow past this. Okay, so now let's change gears to something else. So we should probably do something about the light here. I don't think I need it to be this dark. I'm okay with it being this dark, so it's up to you guys. In any case, we're slightly undisciplined. Okay, what we should be doing is continuing on our galaxy survey. Methodically, doing these 20 galaxies we've identified in these, patches of low Cirrus emission, trying to get our graduate students to graduate on time. Instead, what we did was partway through, we could not resist looking at other things. And so one thing we could not resist doing was looking at the Coma cluster. So this is an image of the Coma cluster with intracluster light stretching about 3/4 of a degree in size. This is way more of the ICL than you'll see in any image that anybody has published. So this is unpublished, almost unanalyzed, and I won't be talking at all about it today. Okay? Instead, what I'll be talking about is a serendipitous observation made by Peter with his eyeballs. Okay, so Peter, looking at our Coma data, with a view towards analyzing the ICL, noticed a remarkable thing, which is that the Coma field appeared to be peppered with little low surface brightness galaxies that, if they were at the redshift of Coma, would be quite remarkable. Okay, because they'd be about the same size as the Milky Way, but their surface brightnesses being so low, these things would have about 1/100th of the stellar mass. So, without expressing any hypothesis as to whether or not these things really are in Coma for the moment, let's just look at their properties, because I think it's interesting to point out the strengths and limitations of Dragonfly, right? Because when I give these talks, people sometimes walk away with, they're all excited about Dragonfly, but they don't understand that it's a thing that is really pretty specialized. If you want to look at stars, Dragonfly is a terrible instrument. But if you want to look at low surface brightness stuff, it's the best thing going. So let's look at a picture, okay? So these are images of these objects that Peter first identified, and a comparison with some CFHT data we were able to retrieve from the archive. So and these are stretched so that the contrast in the background is the same, okay? So this is a pretty fair comparison. So it's booming in the Dragonfly imagery, these objects. But look at the stars, okay? So you got to identify the regime in which this thing is really effective. Right? If what you want to do is, take pictures of, resolved stars and background galaxies, Dragonfly is terrible. But on the other hand, it's spectacular what kind of signal you get relative to, this is a dinky collection of telephoto lenses. This is arguably the world's premier wide field 4-meter telescope imager. So in its domain, it's spectacular. Okay, so then the next question is, do we believe that these mysterious galaxies are really at the redshift of the Coma cluster? So, Dragonfly versus CFHT. Well, there was indirect suggestions that they were, because we were lucky and were able to, find a archival HST image of one of these things. And if we study the properties of this, it's clearly unresolved. So then one can model whether or not, we would see an unresolved galaxy if it were at a lower distance than the distance of the Coma cluster of about 100 megaparsecs. And the answer is, yeah, we would resolve this thing with HST. And we don't. Okay, so that's, indirect evidence that, at least in the case of this particular one, it's at the redshift of the Coma cluster. So it's in Coma. So as of this week, there's better evidence, at least for one object, which is different from the one I just showed you. Okay, so this is a Keck spectrum published last week. Charlie is a collaborator in this. And for this single object, which required, some effort, a couple of hours, I guess, with overheads on the Keck telescope, we were able to obtain this spectrum, which corresponds to this redshift, which puts it smack in the middle of the Coma cluster. So at least the redshift of the Coma cluster. For the indirect one I showed you before, I find that quite convincing as well. So these two of these 30-ish objects are in Coma. So I think they're all in Coma. Okay, so what does that mean? Okay, it means, I think, that we've discovered a surprising new population of galaxies. So if you plot the central surface brightness of galaxies along this axis and the effective radius along this axis, this is the distribution of objects in the Sloan survey. This is the distribution of objects in the local group, and these are of course obtained by resolved stars, right? So this is why you can go this low. And here are the galaxies that have been identified in Coma, and there's a gap between them that is almost certainly due to selection effects. Okay, so these things are new, but they're not completely new. Okay, so there have been, it's not like we're the first people to ever discover low surface brightness galaxies, but this particular population, if it really is associated with a clustered environment, nobody, I think, has ever seen that before. So that's too strong. I think people have found individual objects, but never a population like this. So I think it's quite exciting. And an interesting way of visualizing this is, this is Gene Brody's everything diagram, okay? It plots absolute magnitude versus effective radius for giant elliptical galaxies, ultra-compact dwarfs, dwarf spheroidals, and these things which we're now referring to as ultra-diffuse galaxies, or UDGs. And they, inhabit a really rather different position on this diagram. So what are they, right? Well, they're low surface brightness galaxies, about as big as the Milky Way, about 1/100th of its mass. They appear, at least on the basis of this preliminary evidence, to favor a cluster environment. How can that be? So I guess I don't know. Okay, the suggestion in the paper is that these are somehow failed galaxies that early on were stripped of some of their baryons as a result of the cluster environment. But I think that's really wildly speculative. And at this point, I think it's just best to say, we don't know what they are. But I would say, and this is, again, circling back, to the notion of, are we actually falsifying a prediction? Remarkably, I think in this case, some people would argue that we are. Okay, because these were not known to exist before. But you can go to, the Millennium Simulation site. You can play around, as we did, okay, with the go-it-all semi-analytical models and explore the absolute magnitude effective radius parameter space in the semi-analytical model and ask if there are galaxies from the simulation that have properties analogous to the things that we've seen. And the answer is sort of. Okay, so when our paper came out, Simon White sent us a polite email saying, "You morons failed to notice that we predicted these things." So did he? I don't know. It's certainly there are some galaxies. If you grid it up and bid it, it's right at the very edge. So I don't know. Okay, but I do think it's interesting that. This may be an example, contrary to what I was saying before, of actually, being able to falsify a proper prediction, which would be spectacular if true. So anyway, here's a glossy picture showing the sorts of things we're doing. Okay, so where do we go next? I've given you a few examples. Clearly the next thing to look forward to, I think, is the results from our proper survey, which you can expect in about a year, okay, where I won't be showing you individual objects, I'll be showing you 20 or so objects. But in the meantime, we're not standing still, all right? So this is where we are now. This is your beautiful Great Harvard refractor. When was this built? Like 1840-ish? Okay, you guys know the wonderful. Okay, so we barely surpassed you, okay? This is, where we are now, but this is where we hope to be in a year. So we have ambitions, and we've secured some funding, okay, to upgrade a Dragonfly from a 10-element array to a 50-element array. So this plan is really in its infancy, and this is a preliminary design. And so Dragonfly Mark III, I guess, because originally it was smaller. Anyway, Dragonfly Mark III will be the equivalent of Yerkes. Okay, it's going to be it's slightly bigger than Yerkes. It's like 1.001 meter. So we just, obviously, that's why we made it this. Anyway, so it'll be the equivalent of a 1 meter aperture f0.38 refractor, which should be the world's biggest. And we're hoping to realize this plan at the end of this year. So I will stop there and I'll just leave up my conclusions. Thank you very much.
So thank you very much for the talk. So questions for Bob?
What's a little bit of how much you can expand the array for systematics?
Well, I'm hoping it's less than 50. I honestly don't know. I think so. Look, what is going to limit us eventually is unresolved background galaxies, right now our limitation on resolution is actually not set by these lenses. It's set by the detector scale of the CCD cameras. So, we've got these 5 micron CCD cameras, 5 micron pixel CCD cameras that mean we're stuck with this 3 arc second resolution. But, these are spectacular lenses. So I did essentially a wavefront analysis of these lenses, and the Stirl ratio is diffraction limited, right? So if the Stirl ratio is greater than 0.8, is greater than 0.8 in a couple of the lenses I tested. Which means that, if we could have better CCDs on this thing, I wouldn't be stuck with this 3 arc second resolution. I could get down to, 1 arc second. In which case I could resolve background galaxies, and that wouldn't be the tall pole anymore. So that's why I can't really answer your question. I'm hoping that this thing, unlike, conventional telescopes, is really very organic. And so when we hit some systematic limit, then we'll just figure out some way to push past it. And so, so I think 50 is very safe, but whether or not it makes sense to build a LSST size one, I don't know. I think probably not.
Now, I'm just curious about these low surface brightness galaxies in Coma. How are they distributed relative to the? Do you know anything in that?
A little. So perhaps I can just show you. So they're distributed in a way that seems to avoid the center.
Okay.
Okay, so but here's the
Can you see them in the center?
That's the problem. Okay, I'm really worried that this is just purely a selection effect, right? And that we just wouldn't be able to see a diffuse little galaxy, with I showed you the ICL, yeah. So they're not in the center, but they're on the line.
Have you thought of making a version of this telescope to fly on the space station? I mean, you could do Hubble if you had a good detector.
Yeah, so we have thought about nanosats and things like that. But the ethos of this thing was, meant to be a hobby. And so it is. It's wonderful to see it spiral out of control. But the issue with the nanosat, so that was the first thing. Just put one of these things in space, is telemetry, right? So if you can get the University of Toronto, and I'm sure Harvard, has an aerospace department that can put anything in space in a year or two for $1 million or so, provided it's a 10-inch by 10-inch by 10-inch cube, and it takes like less than 20 watts of power. That's the conventional, nanosat or CubeSat on space and power envelope. So, you could cram a camera in there, but the problem is then telemetry, because you take a picture of something and you have to get that image down to the ground. And the telemetry is such that unless it's a few megabytes in size, it's incredibly expensive. So if, for example, you needed to use the Deep Space Network, that's tens or hundreds of $1 million a year, and so suddenly it doesn't make too much sense to have a $1 million investment. So I conclude that this is above my pay grade, and I would love to think more about it. But right now, I just want to get this project done, and then we will do the ambitious upgrades to space later. But the Swiss are apparently envisioning a not dissimilar low surface brightness imager, and they've applied for funding.
Are these zoom lenses?
Yeah. No. So these particular ones are not. They're fixed focus 400 f2.8s.
And how many elements do they actually have in them?
It's a secret design. Okay. Yeah. So James Graham just
Catch one of them.
Yeah. So, if I were a little more spirited, I would take one apart. But they're $12,000, and really, it's not like I'm going to change anything. But we should X-ray them. Let me see if I can show you. Anyway, somewhere in here I was able to pull up a design from a Japanese patent for the previous generation of these things. And so it's this very complicated 17-element design. So it's a lot of glass. I didn't count air glass surfaces because I'm sure that's changed with the design, but it's a secret.
Be a lot worse with a zoom.
That's what I was thinking. But even where's the market for these things besides sports photography?
Oh, it's amazing.
Nature photography
Yeah.
and paparazzi.
But they don't want zoom. They're satisfied not to have zoom.
Yeah,
I-
well, there's 100 to 300 millimeter zoom lenses that you
Yeah.
can mix, but above 300 they tend to all be prime.
So for I wondered the same thing. Why would anyone care about these sub-wavelength coatings? So apparently, it's sports photography is what drives it because you're trying to photograph athletes against background light, and so apparently, you can sell a photograph for $20,000. So the cost of a 12K lens is no big deal. So anyway, there's a substantial market, but it ain't us.
Yeah, you'd think you'd be better off with like 4 lenses in there instead of 17.
Oh, for sure, yeah.
And that ought to be perfectly possible to actually do, to actually fabricate if you could get these coatings on.
Yeah. So I've thought a little bit about this. So it's like with everything, it's a trade. Okay. So if you want to go with, say, a Petzval, where it would be, you could get this sort of performance. It would be slower and it'd be longer. So you wouldn't be able to cram quite as many on these. These are high-end commercial amateur mounts. They can hold like 300 pounds, but it depends on the torque. So if your goal is to get as much glass on one of these mounts as possible quickly by just writing a check, then this is the way to go. But I think if one was willing to go back into the mode of doing this more thoughtfully than a couple of professors as a hobby, then I can well believe that coming up with a bespoke optical design and talking to Canon and seeing if one could partner with them on the coatings would be the way to go. So, yeah. So I think that in general, the less glass, the better. But you want to have this is a 6-inch telescope that's this big, right? And if you just want to buy a 6-inch telescope, a Petzval, it's that big. So torque's a lot bigger on one of these mounts.
How do you do the color filters? Are they coded also?
Yeah. Oh, that's a wonderful question. Yeah. So to answer. So let me back up a bit. So right now what we've got are Sloan GNR filters, and those are not coded. And we were originally worried that we would be doomed, because of this. And so we were, originally we were doing our imagery by, pulling out the filters completely or using, Canon's special white light filter. But it turns out that it's not the tall pole because not every optic in that optical train contributes significantly to the ghosting and the scattering. And so where Canon has, I guess because these guys are pretty clever, where they chose to put the filter, which is not out of pupil, that's another problem, is not ghosting very significantly. So I'm hoping that, and I think that the filter is right near the element that's got the magic sub-wavelength coatings, because not all elements are coded this way. And so it just appears to be pretty reasonable. but it's not perfect. So we took pictures of, if you can look at the paper in PASP, we took pictures of Venus at minus, when it was like minus 4.5 magnitude, and you can definitely see some ghosts. So it's not perfect, and I think that the from the size of the ghost, that's coming from the filter. So it's an imperfect universe. It's I would certainly love to have all of these elements coded, and I'd really love to put the filter on the front, but we're not there.
Let's thank Bob once again.